Hello and welcome to another episode of Oxford Online Maths Club. My name's James and today I'm joined by Jonah. Say hi, Jonah.
So,
So Jonah's a first year maths student and we're going to do some mathematics. First though, I want to say hello to people who have joined us live in chat. So hi to Rebecca, Ross, Raphael, Maya. I've seen, who have I missed? Hi to Athena, hi to Anonymous and Celia and other people who have joined us in chats live. If you're watching and you would like to join in with the live chat, you just need to go to slido.com and type in the event code OOMC, which is short for Oxford Online Maths Club. I'm recognising a few names from the open days, which we've done over the last couple of weeks, I think. Possibly. Or maybe people have just got the same names as people at the open days, which is nice. But yeah, jump in the Slido if you want to join in. There's also a link on the Maths Club website. If you've joined us from the Maths Club website /r/club, then you can click a link there to join the chat, which should be working. Yeah, hi, Chris and person with the username Mew, which I do remember from the open days, unless there's two people out there called Mew. You can put your name in the chat as your own name or leave it anonymous. I think you can switch between the two as well. I think Jonah, you've been in chat before, right? Because
yes.
so Jonah's been one of the students helping out answering questions in chat and talking to people live. I've now got Jonah on the stream. Jonah, how's it been talking to people? How's it been talking to people live?
Oh, it's great. It's really fun to see all great questions.
Yeah, so people ask really good questions. I like the way people can ask questions in here at any point during what we're saying or what's going on, and it's not quite like interrupting. People just ask stuff all the time, and they also like chat to current students. Today we're joined by Flora and Zakai in live chat as well. So we've got Jonah on screen, Flora and Zakai. All three of them pretty much Math Club regulars who've been around doing lots of bits and pieces. Oh yeah, there's the standard A-level question. I should have warned you about this, that without fail, they've asked every single guest which A-levels they did. If you're happy sharing which A-levels you did, Jonah.
Oh, yeah, I did maths, further maths, physics, and chemistry.
All right, okay. That's actually the same A-levels as me. For A-level policy at the University of Oxford, see our open day videos. But in short, 3 A-levels is sufficient. Right, anyway, okay, I'm veering into open day material again, which you've got to stop me doing because I've got about 5 hours of open day content, which I've already done. I will do it on autopilot. We did it we did the open days twice on different Saturdays, so there's now a real danger that I fall into this kind of periodic pattern of just doing open day material again and again and again. I think it says hi to everyone. Somebody has described this team as the best 4, which is, there's lots of subsets of 4 to check, so we'll think about that one. And Maya noticed that I've started putting the name of the guest and the title of your talk in the YouTube title before we even go live. So that's a little sign of what we're going to talk about in a minute. I was going to start with a quick ad and a quick people like polls. People like polls in the Slido, and I like asking the audience questions about how they're using the Math Club stuff. So I'm going to try and meet both of those. I've got a poll about the further reading, which I'm going to run. Sorry, just while people are joining us. If you're joining us live here, join us here. We're going to talk about maths in a minute. I'm just doing some research. So there's this further reading that goes on the Maths Club website after each episode. It's kind of like an old-fashioned blog. It's got links to other stuff. We sometimes set questions in there, or especially if something came up live and we didn't really answer it live, and we come back to it afterwards. I'm doing a quick survey, which you can see below in chat, of whether people always look at it, sometimes look at it, usually or never. If you don't know what it is, it's on the Maths Club website. Or where do I point? I point that way. No, down there. maths.ox.uk/r/club has a link over there to so there's a link to all the previous episodes and some kind of further notes. And it looks like sometimes is winning on this poll, by the way. About 50% of people are like, sometimes look at the further reading. I wonder if that's based on in the chat. I'd be interested to let you know. I'm not going to read all of this out, but I'll be interested to know if people look at the further reading for ones that they're interested in, or if it's ones where we've promised that something will be in the further reading, or like if it's sometimes how do you decide, or if it's just like how your time works out. just trying to think about how I can make the further reading better. Right, okay, that's a little bit of research. Thank you for doing my poll. Yeah, sometimes there's one and all of the other options have drawn neck and neck second place. So that's exciting. Mainly whether I remember or not. it says an anonymous person, which is honest. And that's got a couple of thumbs ups immediately, so that's nice. Right, okay, there's a load of waffle, a lot of me talking. I'm eating into your time. But I suppose we've now got people are here. People have worked out that I ramble a bit at the start. I've got my admin out of the way. Let's switch to what Jonah's talking about today, which is partial differential equations. I'm not going to spoil it. Jonah, over to you. Partial differential equations. What do you want to say about PDEs? Off you go.
Partial differential equations are what I'm going to be talking about today. A lot of you may have heard of ordinary differential equations. They're on the A-level further math syllabus, and they come up various points within A-level as well. They're quite interesting and they're very interesting areas of research that a lot of mathematicians look into. And so I'm going to be talking about something slightly different, which is partial differential equations. And so the main difference is that ordinary differential equations normally occur when you're differentiating perhaps a function of one variable or perhaps a function of several. That becomes slightly more complex. Partial differential equations are a simple way to go about differentiating a function of several variables, and then we can form equations of them. And so towards the end of this topic, I'm going to introduce some perhaps more interesting partial differential equations that represent real life things. And then we'll go about solving some of those and see some cool effects. And so, yeah, we'll get started. So what is partial differentiation? So if we have a function f, we can differentiate it. As many of you will know, we differentiate it df by dx. That's just the same definition of differentiation that we all know and love. What do we do if the function is a function of multiple variables? For example, f of x and y. So that means that the function contains both x and y's, and they're not dependent on each other necessarily. And so x and y are both independent variables. So for example, what about the function f of x and y equals x squared plus 2xy plus 3y squared? What do we do if we want to differentiate that with respect to x? That's what the WRT stands for. Sorry if I didn't make that clear. So what do we want to do if we want to differentiate that with respect to just x? Well, if we want to ordinarily differentiate it with respect to x, that could be a bit complicated, which is why we have this thing called partial differentiation, which allows us to treat any other variable as a constant. And so, for example, in this example, if we want to differentiate partially with respect to x, we've got to imagine y as a constant. And so we can go through and differentiate term by term and see what we get. And by all means, if you guys want to have a guess at what we're going to get at, by all means, have a go. And so I'll go term by term. I mean, I'm sure many of you know the derivative of x squared is 2x. And then we get onto 2xy. And now this is the point where we've got to start treating y as a constant rather than a variable. And if we differentiate a constant times by x, we just get the constant. And hence, when we differentiate 2xy partially with respect to x, we just get 2y. And now we move on to 3y squared. And once again, we're treating y as a constant, and hence 3y squared must be treated as a constant. So when we differentiate a constant, it disappears. And hence we get the solution. The partial derivative of f with respect to x is 2x plus 2y. And now you notice that I've used this weird little symbol here next to the f rather than a normal d. And basically it means the exact same thing as the d we use in the normal derivative. However, this is what we use when we're doing partial derivatives. So don't let it confuse you. It's just a little bit of extra notation. It doesn't mean anything apart from the fact that we've treated the other variables as constants. And so that's how we've got there. Okay, so we're going to move on to some examples. I'll take you through a little bit of...
Just to jump in quickly, because I've seen someone in chat, sorry. So somebody suggested using the product rule on this, and I think it's worth stressing that for the product rule in A-level maths, or in general, I suppose, the product rule is when we're thinking of both things varying at the same time. So on that x-y term, if we were in a situation where x and y were both varying, if they're both functions of something else that we're differentiating with respect to, then yeah, we'd use the product rule to differentiate them. This thing that Jonah's doing is kind of subtly different. That we've got like x is varying, but we're keeping y constant. So it kind of is a constant, just a tricky constant 2y multiplied by x. So it's kind of different from the product rule because one of the things isn't varying, which is kind of a bit different. Also, that 3y squared term is then kind of totally different to differentiate that with respect to x if you're treating y as a constant versus at school if you differentiated something like that with respect to x, just as a normal way to differentiate it with respect to x. It's a little bit different. There's sort of x and y are playing very particular roles here. Okay, I think I might have made that more confusing by adding in an extra paragraph. Sorry. And there's a discussion in chat about what the name of the curly D is. Zakai in chat, one of our students, thinks that it might be a lowercase delta. I think it's not, but I don't know what it's called. So I'm unlikely to win that argument. I'll go and look it up. In LaTeX, it's just \partial, so it's not a clue. Sorry, I've interrupted just before you show some other examples. Do you want to carry on? Sorry.
Yeah, sure. Oh yeah. So yeah, like James said, that yeah, we treat the y as constant, and I'll go into the geometric interpretation of that in a little bit. And basically, we're going to consider the derivative of a surface, but we'll just do it like parallel to the x-axis, and so the y will be maintained constant. But I'll go into that with a bit of a more explanatory diagram in a second. So let's do an example. Okay, so I thought I'd put this on there as a reminder for some of you, or some of you may not know, that the derivative of sine x is cos x. A little interesting fact that you probably know from A level, or maybe from some further reading. So I've got a little question to see if you guys can do it. Can you guys work out the partial derivatives with respect to x and t separately? The partial derivatives of sine x minus t. So give you guys a second to have a go at that one. Yeah, key thing, just remember that when we're partially differentiating, for example, say I'm partially differentiating this with respect to x, I've just got to imagine t as a constant. And I mean, this one's perhaps slightly complicated in the sense that maybe it hints at the chain rule and stuff like that, but give it a go and see what you come up with.
We did an episode on the chain rule. I think it was one of my episodes, about episode 7 in season 1 for chain rule fun. Never know whether people have seen this sine x cosine x fact at this stage or not. I guess let us know in chat if you want to talk about derivatives of sine and cosine. If you've just seen that for the first time, maybe you're one of the people who watches and you're in year 11 or equivalent, and you've just learnt this fact for the first time. Let us know in chat and we'll talk about it. Oh, and I've turned off replies, so hang on, let me fix that.
Have people had enough time to have a go at it? People happy? Move on to the answer. Actually, I guess I'll move on. So as you know, the derivative of sine is cosine, and so when we partially differentiate sine of x minus t with respect to x, we treat t as a constant as if it were any other constant, and hence we get partial derivative of f with respect to x is cos of x minus t. And now when we partially differentiate f with respect to t, we're treating t as the variable and x as the constant. So we're basically partially differentiating sine of minus t plus constant stuff that doesn't matter. And so you might be able to just do this for inspection, or if you wanted a more analytical proof of this, you could use the chain rule. But the answer is partial derivative of f with respect to t is minus cos of x minus t. And congratulations if you got those correct. If you didn't, I've got another example that you guys can have a go at and see if you can get to the answer to this one. I've gone slightly up a bit. I've gone into 3 variables now, but it's no more complicated because bearing in mind when we're partially differentiating, the other variables can be considered to be constant. So see if you can find the partial derivative with respect to x, y, and t of xy squared z cubed.
Loads of things multiplied together. Someone in chat. So I'm reading out chat because I'm not sure if Jonah can see chat at the same time as seeing slides,
Oh,
even though it's on the screen. I think it's tiny for Jonah. Someone in chat has suggested that it's kind of interesting that the partial df by dx thing you've got and the df by dt thing you've got are negatives of each other. So if you add them together, then you'd get 0. So this f sine of x minus t. Someone in chat says is an example of. They're saying a solution to df by dx plus df by dt. God, all I had to do is read out a message and I got that wrong. A solution to what function can you think of? Df by dx plus df by dt. Chat progressing, by the way, is trying to work out what that curly d might be called. 3 blue 1 brown in chat, perhaps, possibly Grant, is saying maybe del, might be called del. I used del for that upside down triangle thing from vector calculus that we haven't done yet. We haven't done any of that on the stream yet, so you might save del for another day. Yeah. Anyway.
I guess I've got the solution here.
Lillian, people, George, and an anonymous person with a thumbs up are going for this on your derivatives. Somebody with the username Matt Parker has worked out how to typeset. Oh, has that turned up on stream? Has that worked? Yeah, Matt Parker, user, has worked out how to typeset the curly D shape. Goodness knows how you do that. Maybe it's just called partial, by the way. Cool, go for it. I think they've had a go.
Yeah, I would like to just like say to have pointed out that f equals partial f with respect to x, partial f with respect to t added together is a great example of a partial differential equation, and that is one solution that is really good, and we're going to go into how to solve a few of those later. So that's a good spot right there. All right, so firstly, the partial derivative of g with respect to x, we can treat the y squared z cubed as a constant, so it's just x times a constant, and hence we get y squared z cubed. And now if we're doing it with respect to y instead, then we've got a quadratic term of y times constant, and so we're going to maintain the constant, and the y squared is going to become 2y, and so we get 2xyz cubed. And finally, we've got a cubic term for z with xy squared constant, and so we're going to get 3xy squared z squared. And hopefully everybody's happy with how I did that. Let me know if there's any problems, and I can talk through them in a bit more detail. Everyone's good with that. We can move on to perhaps like what could be considered a geometric interpretation of a partial derivative. It can get slightly more complicated because I'm going to do the geometric interpretation of a partial derivative of two variables. But obviously, we can go into many higher dimensions if we want, but I just can't draw a graphic of them very easily, so I'm going to stick with two variables. So we've got z equals f of x and y, and some of you may know that this is what we can call a surface. So it's like a two-dimensional thing that goes within three-dimensional space. So it's basically, if you've got a piece of paper, you can wiggle it, wobble it, whatever you need to do, that is a surface, and we can represent it in the form z equals f of x and y, where x and y are both variables in 3D space. And so what does the partial derivative of f with respect to x mean? We know in 2 dimensions, if we've got y equals f of x, the derivative represents the gradient at the point. But problem is now we're dealing with a surface, and surfaces don't have a specific gradient. They have more of a tangent plane. But what the partial derivative of f with respect to x is, it's the gradient in the x direction at that point on the surface. So for example, if you can imagine choosing your point, which is where you're going to sub in your coordinates, and then you're drawing a line that's tangential to the surface and also is going in the same direction as the x-axis, and so it's going to be perpendicular almost. If I was going to say, it's going, if you projected the line into the xy plane, it would be perpendicular to the y-axis, but perhaps that may be making things unnecessarily complicated. So it's just it's the
how's your 3D geometry, everyone? So projecting is Do you hear the word projecting much before university? I know what you mean about sort of like taking a thing in high dimensions and just sort of squishing it down onto some of the dimensions. Sort of wonder whether, I guess that's like projectors in school move. Sure. What do projectors do? They sort of beam light onto a surface. That's kind of like moving everything over onto a surface a bit. halfway through that, I realised that maybe schools don't use projectors anymore. Maybe it's all enormous touchscreen computers, and I'm out of date and old.
Still used them when I was in school.
I like this geometric picture of what derivatives mean. I think
Yeah.
in what you're going to do next, so in the bit we're doing about partial derivatives, we're probably not going to do them geometrically, right? But
Yeah,
there is
we're
this
not.
kind of there is at the back of your mind, maybe there's this kind of geometric idea about this has got something to do with gradients of a surface, in the same way that like derivatives of functions has something to do with the gradient of the tangent at that point. But that doesn't often help you when you're actually solving differential equations. They're kind of different compartments of your mind.
Yeah, so for example, so we've got partial derivative of f with respect to x gives us direction in x direction, like James said. We could also work it out in the y direction if we did the partial derivative of f with respect to y, just as easy. And with those two pieces of information, if you want to go into a bit of higher dimensional vectors and you can get into a bit of nice geometry, you can work out the tangent plane because you know the gradient in one direction, the gradient in a perpendicular direction, and as long as you've got the gradient into linearly independent directions, you can get a nice tangent plane, which will tell us exactly the plane that basically touches the surface at that point. But that might be getting a bit too complicated and unnecessary for this talk. So I'll digress. Okay, so we'll move on to a bit of partial differential equations, which in the simplest possible terms is an equation with partial derivatives in. And so I thought I'd give you guys the opportunity to have a go at this one here. So we've got partial derivative of f with respect to x is equal to 2x, which is partial differential equation like any other. And you guys have a go at solving this one. Try not to don't overcomplicate it. I promise the solution is not something insanely complicated. It's quite nice and simple and understandable. A good recommendation to solving this would be consider if it was instead not the partial derivative, if f wasn't the function of both x and y, if it was just the ordinary derivative, if f was just a function of x, and then maybe go from there.
Chat is so fast. People in chat are having a go. Oh, and they've got different answers.
I
So I
can't see
guess
what any of the
so people in chat so far, I've got four. Yeah, so integration. Somebody's put integration reaction face. And I should give credit to I think it was Josh about 10 minutes ago who had just seen partial differentiation and said something in chat that was like, if there's such a thing as partial differentiation, can you also do partial integration? Josh, look, here it goes. Here we are. So they're trying to guess what could f be if the partial derivative with respect to x is 2x. The answers we've got so far are amazing. X squared plus y squared is in there. F equals x squared was the first thing people say because it's the quickest to type. F equals x squared plus c. X squared minus 440 no 4 minus 4,425,411 y. So if you want a kind of linear y term there, or somebody's put f of y or c y to the n, like how many y's can you have? Molly wants. I'm not even going to read that number out. 363. Is that pi? Oh, there is a pi in there, right? Okay. Is that pi? George has given pi or something in y. Yeah, okay. So consensus is x squared plus something.
Well, I mean, everything I've heard, so most of the things I've heard are actually correct. We're trying to look for a general solution, but I've heard a lot of non-general solutions, which are still solutions, but we want a very nice general one. Yeah, I guess the key thing to remember here is when we're doing partial integration, I'm not going to call it partial integration because that's not such a commonly used term. When we're doing our partial integration or normal integration for that matter, we always get a constant of integration. And perhaps it's worth considering what our constant, I'm not going to call it a constant of integration, what our something of integration might be in this case. Well, I'll go about solving it, and it's 2 steps. So the first thing to think about is, well, we can integrate both sides with respect to x, as someone said very intelligently in the chat. Nice simple way of solving this. We integrate the left-hand side, we get f. We integrate the right-hand side, we get x squared plus a constant a. Nice and simple. However, if we go into this partial integration thing, I'm slightly enjoying the partial integration idea now. We've got so we've got partial derivative of f with respect to x, which meant that we treat any other variable as a constant. And I'm sure some of you might have realized that meant, or as some of the answers in the chat said, that meant that our constant might actually contain y. And you guys are completely right. It does contain y. And the fact is that instead of having, say, a constant of integration now, we kind of have a function of integration. Just move that in right there. A as a function of y. I thought I'd do a nice little bounce thing to really bring it together. Yeah, so instead now we've got our function of integration, because any function of y, if we differentiate partially with respect to x, is going to be treated as a constant, and hence is going to disappear, and we'll get 2x. And so any function of y works in that situation, and so we've got a function of integration. And the mathematical term, I guess, for this would be arbitrary function. If you want to use that, it's basically any function works right here. And so this is a key idea within differential equations. And we're going to move on to a slightly more complex differential equation. I say slightly more complex, a very nice complex one, because we want to have a bit of fun with this. And so I'm going to move on to a nice complicated one, but I think this idea is important to bear in mind. And so moving on to something called the heat equation, which is going to be the main part of this talk. And so the heat equation is a partial differential equation which basically describes the temperature in a conducting rigid rod. And so that is just a rod in which the temperature is going to vary one-dimensionally. So for example, the temperature is only going to vary along the x-axis, for example. And so we'll have one end of the rod lying at one point, the other end of the rod lying at the other point on the x-axis. So we have our rod there, and we want to just look at how the temperature is going to vary as we vary x and as we vary little t, which stands for time. And so we can derive a partial differential equation for our temperature, which we can find using various mathematical models, physical equations, something called Fourier's law. If you guys are interested, there's some very interesting formulae in maths, such as Leibniz's integral rule and the fundamental theory of calculus, which goes into deriving this equation. But I'm not going to go into that now. Anyway, the heat equation we get is this thing right here. It's the partial derivative of T with respect to time. The partial derivative of temperature with respect to time is equal to kappa, which is a positive constant, which is called the thermal diffusivity, but don't worry about it. It's just a constant that we relate to a material. Kappa times the second partial derivative of temperature with respect to x, which is our position along this x-axis. And so what we're going to do is we're going to have a look at how we would go about solving a differential equation of this form. And this one's slightly more interesting because not only is it a bit more complicated, but it actually has relevance in a real situation. And given some initial conditions or boundary conditions, so these are conditions which we can put temporally and spatially on our rod, and I'll go into those a bit later, but they basically allow us to solve this equation. And I thought I'd put a little diagram here, and I think James got some better graphics, much more efficient, like nicer stuff to make on MATLAB. So I thought I'd just quickly explain what we're trying to find. So for example, this is a diagram which represents temperature with respect to x. Ignore over L is just a scaling factor. So this shows the temperature with respect to x. And as you can see, we've got this weird blocky shape at the start. And as time increases, which is in the direction of the arrow on there, we can see the graph slowly mellowing out, which is basically saying that at the start we have this weird blocky shaped temperature graph, which shows that at this point here there's a really high temperature, or like there's a temperature of 1, and at the rest it's a temperature of 0. And over time the temperature is going to spread out. And we're going to look at solving something very similar to this, but I think James has a nice graphic that would be very helpful here.
Yeah, so what I did, quick insight into my PhD. So this partial differential equation gives an idea about how the thing changes with time in terms of how it changes in space. So I gave that to my computer to say, okay, we've got this rule about how this thing changes in time that depends on how it changes in space, at any given time for any given starting function, I'll just work out what the second derivative is by doing some little derivatives on my function, and then that gives me a rule about how to evolve it, how it updates, which is kind of what's going on in these red lines, right? There's some second derivative to this curve, something that happens if you differentiate it twice with respect to x, and that gives you a rule for how to update it. I gave it to my computer to have a go at integrating, or to have a go at not really integrating, just sort of adding. And I got a video out like this. Let's see if I can play a video on the live stream. I haven't tried that for a while. No, yes, okay. Brilliant. Here we go. So this is maybe not the most exciting of graphics, but I've got this kind of starting profile of what the temperature looks like, and then it kind of spreads out. So I've got this kind of blob of temperature where it's hot in that bit of the rod, and then over time it sort of spreads out. So here my computer's working out the second derivative. It's worked out that the second derivative is not very much, so it doesn't update the heat very much. It just gradually settles down. Oh, that's just started again. Apparently that's one of those looping videos. Okay. So I've got this thing that kind of gradually cools down and settles down. And incidentally, at the same time, my computer's heating up. It's just turned on all the fans, so that's exciting. So there's this kind of way that it evolves over time. That's just giving it to my computer, though, getting my computer to kind of approximate everything. We're going to see how to try and solve that. Good. Right. Okay. Let's switch back slightly. There we go.
Good. So we've got our heat equation, and we're going to go through how we would go about solving this, which is a nice fun thing that you guys can try. We're going to use a few A-level techniques, some of which I'll go over briefly, some of which I won't. And the ones that I won't, don't worry if you don't understand where I got them from. If you haven't covered them at A-level, you may cover them at A-level in the future, or you can do some extra reading. I promise you, nothing that I'm skipping over is too complicated to learn at home on your own. I'm just going to skip over it because I'm sure you guys don't need me to teach you A-level maths. So, separation of variables, which is a technique that many of you may know from A-level, but I'll explain how we set up our problem, and then I'll go into how we solve it using separation of variables. So we've got our rod of length L, where L is any number we want. I mean, we're going to assume L is positive, but it doesn't really matter. So we've got one end lying at x equals 0, and the other end lying at x equals L. And so what we need to do is, with some conditions on this rod, so for example, firstly, we'll consider something called boundary conditions. And boundary conditions define certain physical properties of the rod in terms of space. So these are conditions that don't vary with respect to time. They're constant with respect to time. So for example, these boundary conditions that I'm going to set up, this is an example of one, is that the ends of the rod are always going to be at a temperature of 0. And it doesn't really matter what temperature is measured in. But so this is a boundary condition because it only mentions spatial terms in terms of the temperature of the rod. It doesn't change with respect to time. So in all time we go through, the temperature at the end of the rod will always be 0. And I'll show you how we use that in a second. We also have something called initial conditions. And initial conditions are conditions which are something very specific with respect to time. They're known as temporal conditions, whatever we want to call them. It basically describes the temperature of the rod at the start. And not a very complicated thing, but we can have some very interesting ideas about how many boundary conditions and initial conditions we need for any given partial differential equation. And so this one here, we're going to use, we only need one initial condition. And so we say, for example, that T of x of 0, which means the temperature at time equals 0 across the whole rod. So that's at any x is equal to this function of x, which is basically the most vague way of saying that our temperature at the start is a function of x, which is quite obvious, seeing as at the start we don't vary on time because we're talking about time equals 0, and so only x is going to vary, and so we have T of x of 0 is equal to f of x. And now we've got quite an interesting technique called separation of variables. Some of you may have met this at A-level, some of you may not. I'm going to outline it briefly. Some of you may not recognize it by name, but may recognize it by what we do. So separation of variables is where we can consider, well, in this situation, we're going to assume our solution for the temperature, so the function of T of x and T, can be written as a function of x, f, multiplied by a function of g, t. And this is not true of all functions of x and t. Like, for example, I mentioned one earlier that can't be written like this, where I think it was a function of x and 1. So we're going to make this assumption that it can be written in terms of a separable solution. And we're going to use this to obtain solutions for our heat equation. And then we're going to do some cool stuff to show that to find non-separable solutions. But so we're going to make our assumption that our function of temperature, so our solution that we're going to come to at the end, is a function of x, which we've denoted f, times function of g, function of time, which is g. So I'm just going to quickly outline separation of variables just for you guys, so in case you're interested. So this is separation of variables, which you may recognize from A level. It's about when we have a function, for example, dy by dx equals f of x times g of y. So when we have an ordinary differential equation where we have a function of x times a function of y, what we can do first is divide very carefully by g of y, ensuring that g of y is not 0, very important. Next, and I feel I need to stress this quite thoroughly, that this is one of those situations where we treat the derivative as a fraction, despite the fact that it's definitely not a fraction. So we can't multiply by dx, but we're going to multiply by dx anyway, because it's calculus, so who cares? And so we get this, so we're going to multiply both sides by dx and integrate. And I do want to stress very carefully that you can't normally treat derivatives as fractions, but sometimes you can. And going into when they act as fractions is a whole different thing. But anyway, so we've got on one side a function of 1 over g of y, which we've integrated with respect to y, and on the other side we've got the integral of f of x with respect to x. And we can integrate these normally because the left-hand side is function of y, the right-hand side is function of x. That's absolutely fine. We know how to solve those, and this is called the technique of the separation of variables. And we could just perform this integration, and this will give us an implicit solution, which means a solution which is a solution with no derivatives in, but is not written in terms of y. And an explicit solution is one that's written in terms of y. We won't always be able to rearrange this to get a solution for what, like y equals a function of x, but sometimes we can. That's called an explicit solution. Anyway, just wanted to mention that briefly so that you guys have a general understanding of separation of variables. Apologies if you already understood that. I just want to point out in the top right corner is the heat equation, because we're going to continue on solving the heat equation, and it's important to remember what it is so that we actually know what we're solving. Okay, so we've decided to go about this method where we're going to assume that t can be written as a function of x times a function of g. And so we want to calculate each part of the heat equation, and then we can substitute it in and try and solve it. And so on the left-hand side, we have the partial derivative of t with respect to time. And that obviously we can't do straight away if t is not we can't do using ordinary differentiation if t is a function of x and t, but we can do if it's a separable function of x and t. And so, for example, here, when we by all means, if you guys want to have a guess of what the partial derivative of this with respect to t is in the chat, by all means, give it a go. I'll give you guys a second just so you can have a guess at what we're going to get when we differentiate this partially with respect to t.
You reminded me. I might put separation of variables for sort of A-level maths stuff in the further reading, or I might put something there. Somebody's asked for a product rule in the further reading, so hey, maybe we're doing a bit of A-level learning or revision or something like that. Oh, people are going for it in chat. There's a comment that's getting lots of thumbs ups, possibly the most popular thing today. While people are thinking about what happens when you differentiate these things with respect to t, oh, they're going for it. It's great. All my teachers say that derivatives can't be treated like fractions. It's just disappeared off the bottom of the screen. All my teachers say that derivatives can't be treated like fractions, and then they treat them like fractions. Why can we use them like this even though they're not fractions? And it's a really good question that, we sort of did it in that example there. We sort of said it's not actually a fraction, but when we integrate each side, we're kind of fine. There's secretly some great mathematics involving oh, thank you, whoever highlighted it, thanks. There's secretly some really great mathematics to do with matrices and partial differentiation going on. It kind of ties together things we've previously done on the Maths Club with stuff we've done today. I don't have time to say it now. Essentially, it works out. I'll put something in the further reading. There'll be a small paragraph in the further reading about that question because it's a good question and needs a proper answer. Essentially, derivatives actually work like matrices, and 1 by 1 matrices happen to look like numbers. So that when you do the inverse of a 1 by 1 matrix, that's just like turning a fraction upside down. So you get away with it in that case. Inverses of bigger matrices are nothing like fractions, and you don't get away with it. So, okay, and I'll put something to that effect in the further reading. Right. Okay. Sorry. That's the third time I've interrupted with just here's some other maths that chat's talking about. They've also had a go at this. They've mostly said f of x g prime of t to just differentiate that g. Leave the f alone. Yeah, so yes.
Right there.
Because the f of x is quite kind of the point again of this is not quite the product rule because that f of x doesn't depend on t. So it's kind of a distraction. It's like a constant out the front. As you change t, f of x doesn't care at all.
So yeah, you guys are perfectly correct. Yeah, we ignore the f of x because it's just a normal function of x, and we're going to then ordinarily differentiate g with respect to t, which is what we mean when we say g prime. So that's just dg by dt. So yeah, exactly right, perfect. Then I mean, you guys are more than welcome to have a go at working out the second derivative of t with respect to x, but I'm just going to say it because you guys have clearly shown that you understand this perfectly. The second derivative with respect to x partially is just going to be f dash dash times g because we're going to ignore the g because it's not a function of x, and we're going to differentiate the function of f because it is. And so, okay, we've got this, and we can now substitute these into our heat equation. And so when we put the partial derivative of t with respect to time on the left-hand side, we're going to get f g dash, and on the right-hand side, we're going to get kappa f dash dash g. And so that's what happens when we substitute it in. And this, and then I'm trying to explain how we slowly get our heat equation into something that's more manageable and something that we can actually go about trying to solve. And so, what we can assume basically we're looking for t equals f times g, and we don't want boring solutions because boring solutions such as t is equal to 0, because that's not very interesting. It doesn't tell us much about the rod. We don't want that steady state solution. What we're looking for is something more interesting that depends on both x and t. And so we're going to make the assumption that f times g, which is our t, does not equal 0. And we're going to have to bear that in mind because at no point can it equal 0, but we're going to make that assumption because we don't want boring solutions. And so we can divide by f and g, and hence our heat equation becomes this, where we've substituted into the heat equation and we've divided by f and g, and that's all we've done. And so this is our heat equation, and notice that we've got something on the left-hand side, which is like the second derivative of f over f, and on the right-hand side, we have the first derivative of g with respect to t over kappa g. And so that is quite important. So a key thing to notice here is that, okay, we look at our left-hand side, and we've got the second derivative of f over f. They're both functions of x. And so are there any t's on the left-hand side? No, there's no t's on the left-hand side because they're clearly both functions of x. And so, okay, left-hand side's got no t's on, it's just a function of x. Right-hand side, we can look at the same thing. We can go about considering it the same way. We've got function of t on the numerator, function of t on the denominator. I can't see any x's there. That doesn't look so much like a function of x. It's just a function of t on the right-hand side, and so there's no x's on the right-hand side. And on the left-hand side, it's completely independent of t. On the right-hand side, it's completely independent of x. And because they're equal, that means both sides must be completely independent of both x and t. And this is how we go about solving separable equations, because we can separate them into two sides, both of which depend on different variables. And hence, because they're equal, they depend on neither variables. And so both sides are not dependent on x or t. And some of you may want to have a guess at what that means both sides are equal to. I'll give you a second, because basically on the left-hand side, it's not a function of x or t, right-hand side, not a function of x, t. So these must be equal to something that's not a function of x or t. And bearing in mind that there are only variables, anybody, like, you're welcome to have a guess at what that means this is equal to. You're welcome to make some suggestions in the chat.
Yeah, so this is kind of the, I guess, recap while they're typing about what's the consequence of this way of writing it. This is the key idea about separating variables. Jonah had a good guess about, let's just guess a function for what the temperature could be, and then did some rearranging. And someone called ultra product says a constant. Both of these some constant? In fact, two anonymous people said that a temperature or a constant. Yeah, some sort of. Some people want it to be equal to kappa because it's independent of x, dependent on t, and I guess it could depend on kappa. I think it could be something else that depends on kappa, but it's importantly, in terms of x and t, it doesn't depend on x or t, right?
Yeah, you guys are exactly right. It is equal to a constant, and we're going to call this constant minus lambda because we're doing applied maths here, and so we like our constants to be positive. And I'll go into in a little second of why this side has to be negative. But for now, just know that that side is therefore equal to a constant, and because both sides are equal to each other, they're both equal to that constant, and hence we can separate these out. And so what we can do is we can consider firstly f dash dash over f equals minus lambda, and we can write that as an ordinary differential equation. And similarly, we can do the same with the other side. So we arrive at this. And hopefully you guys can all see how I've arrived there, purely because we've now got three equal signs, and so we can just consider them independently. So we take the left-hand side and the right-hand side, and those two are equal, and then we can take the middle, which is the g thing, equal to the right-hand side, and then we get the second ordinary differential equation, which is g dash equals minus lambda kappa g. And again, so we've arrived at this, and this is great because for those of you who've done differential equations in further maths, this is exactly of the form of something we know how to solve. It's really useful, absolutely great, and so we can go about solving it. And I'm more than well, you guys are welcome to make suggestions of what the solution is in the chat. If you guys have done differential equations, no worries if you haven't. I'm not going to go over how we go about solving this. It's A-level material, so by all means, if you don't know how to do it already, go and have a little read. I'm sure I could put something somewhere or something like that about how to solve differential equations. If not, it's in the A-level textbook. And so here we have our ordinary differential equation, which is the second derivative of f with respect to x plus lambda f equals 0. And this is going to have solutions. I'm just going to go and put the solutions here. Congratulations if you worked out what they are. It's going to be f equals I've used the constant omega, and that's only because when we solve this using A-level techniques, we're going to get the square root of lambda involved inside these cosine and sine brackets, and I don't really want to be dealing with square roots, and they're kind of annoying to type in LaTeX. So we're going to call lambda equal to omega squared. And so we've got our f is equal to a cos omega x plus b sine omega x. And you may be wondering why we've got two constants. This is all something that's covered in A-level, and I'm sure you'll cover this stuff later on if you choose to study something mathematical at university. But yeah, this is our solution for f. Okay, and so this is great. We've worked out 1/2 of our heat equation because we know T that is equal to F times G, and we've worked out F. However, that's quite a lot of variables in there, and we don't really like variables because they don't give us exact numbers, which is what we want when we're trying to solve for temperature in terms of space and time. And so we remember boundary conditions. Boundary conditions are very, very important, and they're something that I mentioned earlier. They basically said, remember we said that we're going to keep each end of the rod at a temperature of 0, which means that T at x equals 0 and T at x equals L is 0 for all time. And what we learn from that is that f of 0 and f of L must be equal to 0 because g of t can vary as when f is equal to 0 or f is equal to L, but the equation is equal to 0, and we don't want our g equal to 0 because if g is equal to 0, we've got a trivial solution. That's boring again. And remember at the beginning, we made the assumption that we're not going to have g is equal to 0. So we've got f of 0 is equal to f of L, which is equal to 0 from our boundary conditions. And now we're going into how we use boundary conditions to begin to solve this equation. And so we can substitute these into our solution for f. And when we substitute these in, very simply, when we substitute in x equals 0, we're going to get a equal to 0. And when we substitute in L, x equals L, we're going to get b sine omega L equals 0. Okay, great. So we've got that. And so we can begin to go about understanding the value that these constants are going to take. Okay, so we know that b sine omega L is equal to 0, but we're going to need to solve that. If b is equal to 0, once again, f is going to be 0, and so we have trivial solutions, which basically mean boring solutions. So we're going to let sine omega L equal 0, because that's much more interesting, and that allows our b to vary. And so we're going to have sine of omega L equals 0. And some of you may know the roots of sine, and others of you may not. Anyway, so we know we need to solve this equation, omega L, sine of omega L equals 0, bearing in mind that both omega and L are positive. But apart from that, omega has not been defined, so it can be equal to anything we need it to be. And so we can go about solving this equation, and some of you may know the roots of sine are integer multiples of pi. And so that makes omega L equal to any integer multiple of pi that's positive, bearing in mind because omega and L, omega is a square root of lambda, and L is the length of the rod. So they both need to be positive. So we get that omega L equals to a multiple of pi, we call n, and that means omega is equal to n pi over L. Okay, and now we can substitute this back in, because remember, we then have that f is equal to b sine omega L. And now we know what omega is. This tells us our f. And so we're one step closer to solving our heat equation. So we found that we solved our differential equation for f and found that it was a sine something plus a cos something plus b sine something. The a is equal to 0. The omega is equal to n pi L. And so we get this. And from this, we now know what lambda is. Lambda is equal to n squared pi squared over L squared. And you may remember a while back, I used minus lambda instead of lambda. That's because in applied maths, we like our constants to be positive. And if we use lambda equal to 0, or lambda equal to, equal to lambda as a positive constant rather than minus lambda, we've got a trivial solution. We'd have got f equals 0, which we don't want because it's nice and boring. So we now know that lambda is equal to n squared pi squared over L squared, because lambda is just equal to omega squared. And now we can go back to our differential equation from G from a while back, which said that G dash is equal to minus lambda kappa G, which we got by our separation of variables technique. And once again, we're going to use A-level techniques to solve this, which I'm not going to go into because, you guys can by all means go into that yourself. But we get G is equal to C times exponential of minus lambda kappa T. I just want to make it clear for any of you that might be confused that the exp represents the exponential function. It's the same as saying e to the power of minus lambda kappa T. Just this fits better on the page. Okay, so we found f, we found g, and yeah, I realize that we initially assumed our solutions are separable, so perhaps we're going to need to do something else. But the fact that we have f and g means that we do have a solution for t. It may not be the only solution. It may not be unique at all. There may be infinitely many. We do have a solution of t, and actually there are infinitely many, because we've shown that this is a solution for any n, because any n will give an integer multiple of pi, which will go into sine and make it 0, which will satisfy our boundary conditions. So we've got t is equal to bn, which I'm going to explain in a second, times sine of n pi x of L times the exponential of minus n squared pi squared kappa t over L squared. Now that does sound like a mouthful. But,
I'm going to do one of my legendary recaps, just because someone.
That's probably a good idea.
Someone says, "Parents, how do you relax in your free time?" Me, colon. There's a lot of maths on screen. There's been a lot of steps. The plan so far is heat equation in the top is the thing Jonah's trying to solve. This is a differential equation. We had some examples where you kind of guess. Oh, I know this one. I can guess what happens when you differentiate that. Jonah had a kind of guess to split it into separate f of x and g of t, and then there were some consequences of that guess that let Jonah kind of prise the problem apart to try and say, well, if it's f times g with the space and the time bit separate, can I say anything about f and g separately? There's this brilliant, pull it apart, say both parts are a constant, and then brilliantly we've got these different problems for f and g. And then there's lots of like university level actually solving for what f and g are. But if we look at this last line, right, this last thing, the temperature here is, okay, some number b of n, who cares about numbers at the front, but there's a sign bit that just depends on x. It's got loads of constants in as well, but there's a sign bit that just depends on x, and there's an exponential bit that just depends on time. So this is the kind of solution that Jonah was looking for, of having a space bit multiplied by a time bit as a solution to technicalities, getting all the constants right, so that it actually satisfies the heat equation at the top. But that's kind of what Jonah's been looking for, is kind of separate space and time dependence multiplied together. I guess this actually looks like, this particular solution Jonah's found is actually like some sine wave in space, that's the space dependence, that decays with time, because there's that exponential has got a minus sign in it, so that's saying things decay with time. So there's a very particular solution, just by guessing things separate out nicely into space and time bits. And there's some consequences about getting all the derivatives right and getting all the constants to work out. But we found this particular solution. It's quite nice. It says if you've got a sine wave, you start your sine wave, n pi x over L, whatever those constants mean, and then it just decays. You've got a wobbly bit with hot bits and cold bits. Well, it all just evens out. It all just settles out, and there's this exponential decay. It kind of already feels a little bit like the graphics we had earlier, the thing just going vloof. Except that wasn't a sine wave. In fact, so Jonah's solution is pretty good, because keeping track of all the constants and being as general as you can, we've had this guess of what the solution is, we've got all these constants in. Jonah's solution has actually got different ends, so it's got different sine waves. So it's not quite perfectly a general solution, but different sine waves. You pick a sine wave like 2 pi x over L, and that's n equals 2. Jonah can say, well, I've got this solution to the heat equation. It's got 2 pi x over L for the sine space dependence bit, and then it's got exponential of minus 4 pi squared kappa t over L for the time dependence of how that one decays. So you give Jonah a sine wave, you get back, hey, I know how that evolves, how that changes over time with the heat equation. So that if you set up a perfect sine wave with hot and cold patches in the rod, then it would bloof at different rates depending on n, with that n squared in the exponential bit. Seems nice. I mean, you've got your solution for different sine waves. If somebody comes to you with a sine wave and says, how does this evolve under the heat equation? Seems like you're good. Do you want to say a little bit just quickly? I know you've got some. There's a little bit to go, but do you want to say just sort of quickly how you might do a kind of general problem, or what if it's not a sine wave that you start with? I'm trying to hint at some theory.
Yeah, I think we'll be onto that in a second. If we're not starting with a sine wave, it'd be a bit more complicated, and the maths can be a bit unwieldy, because we then need to we can. Okay, so we've got this equation, but what happens if at time equals 0 it's equal to anything? And then we go, oh, that's a bit complicated, because we've got anything is equal to this weird constant, and then we don't know if we're necessarily going to have sine and exponentials if our boundary conditions aren't met. But actually, we get some quite interesting theory at university, which basically states that we're quite basically causes and sines jump out of the heat equation very nicely, and this is down to something called the theory of Fourier series, which is very complicated and very interesting, very worthwhile reading into. But yeah, so basically sines and cosines, regardless of the fact that, regardless of how we're starting, of our boundary conditions, they're very intrinsically jumping out of this equation, and almost always part of the solution, which is very nice.
Shall we? I think we need to wrap up in a minute for time. But I think leaving this as a kind of a hint towards this kind of bit of theory that, okay, this was a nice idea, separating out the variables gives you what happens to a sine wave. You know, we could do sine waves. Is that good? But actually, there's this university theory that you can make a lot of functions out of sine waves. Sine waves get you a lot of the way towards building other things. And people in chat are comparing how complicated A-level maths is to other sorts of maths, saying how complicated it is. Maybe we just got too many letters on the slide. Maybe if it was just sine x e to the minus x. That doesn't quite. Yeah, so sine x e to the minus x would work if we kill most of the constants. Then I think sine x e to the minus x, ignoring boundaries and stuff. Sine x e to the minus x works as a solution to the heat equation. Cool. Right. Guessing stuff. Should we wrap up there? We could put a note in the further reading about other stuff that we could have gone to, but it feels like we're losing the room. Great content. Thank you very much, Jonah. Thanks for showing us partial differential equations, some that we can solve and some that we can guess solutions to. I really like this sort of maths because it's quite closely related to the sort of maths that I did a PhD in. And I think we're going to wrap up there. Anything you want to say to wrap up? Or?
No, just lots of interesting theory to go away and read into. By all means, really good YouTube videos you can watch if you want to see some graphics. For example, green, blue, on brown. They've got some really interesting stuff for this.
Yeah, stuff on heat equation and also stuff on Fourier series. And Molly has given us a fact of the week, which is, until 2005, the picture used in all books and all articles about the mathematician Legendre wasn't a picture of him. It was a picture of a different French person with the same surname, 3 skull emojis. Some textbooks still use the wrong photo. Thanks to Molly for Maths Fact of the Week, which I now expect to be a new feature of the live stream. Thank you, Molly. Right, okay. Thanks for watching. We'll be back for I'll post some further reading on the website tomorrow. We'll be back for the next Oxford Online Maths Club live stream in 167 hours. See you then. Bye. I'm so bad at turning it off. Right, okay. We do this. Okay.